Welcome to the Unit 2, Section 1 video on inductive reasoning. So we're going to start off this section by talking about patterns. When several examples form a pattern and you assume the pattern will continue, you are implying inductive reasoning. Your inductive reasoning is a type of reasoning that reaches conclusions based on observations or past experiences. So observations or past experiences. So what you're doing is you're drawing on things that you know and making an assumption as to how the pattern is going to continue. So for example, in example 1, we have the numbers 102, 96, 90, 84, 78. It may take you a minute or two to look at it, but if you notice, each time we are subtracting by 6. So our next two numbers would be 72, and then another 6 from that gives us 66. Okay, so we are making the assumption here that each number is 6 less than the one before it, which gives us the two that we assume are the next in the sequence. Okay, so for the next one, we have 1/2, then 1, 2, 4, 8. Our assumption is we continue on to 16 and 32 because our past experience tells us that 1/2, when you double it, is 1. When you double that, it's 2. When you double that, it's 4. When you double that, it's 8. And so on to 16, 32. If you are into computers, you know that this continues to 64, 128, 256, 512, 1024. It's all about memory, right? All right, so we can do this not only with numbers, but we can also do it with other things. So let's try the next one. We have Monday, Wednesday, Friday. Our assumption is the next one in this sequence would be Sunday because we're skipping a day each time. We skip Tuesday to go to Wednesday, we skip Thursday to go to Friday, we skip Saturday to go to Sunday. Here we have directional arrows. We have one that's pointed west, then northwest, then north. Our assumption is the next one will go northeast because we're rotating clockwise around a compass. And then we also have shapes such as the ones you see here. So our assumption here is if we've got the top left, then the top right, then the bottom right, our assumption here would be that the next one to be shaded would be the bottom left. So we'll draw in what we think is going to be the next one. So there's our square that's divided into quarters, and we're going to shade in that bottom left piece because that's the one that we assume would be next because we're shading in the corners, rotating clockwise again. And so the one after this, we would return to the beginning of the sequence here, and we would just repeat these 4 over and over. For the next one, we have a triangle. Then that triangle has 3 triangles below it, and then this figure has 5 triangles below it. So our next assumption would be that we would have a triangle that would consist of 4 rows. So 1, 2, 3, 4. And of course, this triangle is going to be just like the one before it, this part of the triangle that's here on top. But then we would have another row that would consist of 7 triangles in total. So that's a little bit of identifying patterns, and we're using inductive reasoning to identify those patterns. Now let's talk about making a conjecture. When making a conjecture, you're using inductive reasoning to draw a conclusion from a pattern. A statement you believe to be true based on inductive reasoning is called a conjecture. Okay? So when we were identifying those patterns above, the conjectures were the items we were filling in at the end. Okay? We can do that on a little bit larger scale. For example 4, we're going to investigate the product of odd integers and make a conjecture. So 1 times 3 is 3, 3 times 5 is 15, 5 times 5 is 25, 7 times 9 is 63, 9 times 11 is 99, 1 times 5 is 5, 3 times 7 is 21, 5 times 7 is 35, 7 times 11 is 77, and 9 times 5 is 45. So we just have a selection of multiplication tables that all involve odd numbers, an odd number times an odd number. And every result that we got was itself odd. So our conjecture is going to be that the product of any two odd integers is odd. For example 5, we're investigating the sum of any two odd integers. So let's do these sums. 1 plus 3 is 4. 3 plus 5 is 8. 5 plus 5 is 10. 7 plus 9 is 16. 9 plus 11 is 20. 1 plus 5 is 6. 3 plus 7 is 10. Almost did the multiplication there. 5 plus 7 is 2. 7 plus 11 is 18. And 9 plus 5 is 14. So you notice when we add two odd numbers, everything we've gotten in these 10 that we did was even. So our conjecture here is the sum of any two odd integers is even. So to show a conjecture is always true, you must prove every instance of it. To show that a conjecture is false, you have to find only one example in which the conjecture is not true. This case is called a counterexample. A counterexample can be a drawing, a statement, or a number. So if we want to prove that something is true, that's going to be very difficult because we can't exactly prove every single instance, especially if it involves numbers, because there's an infinite number of numbers. But proving something is false is far easier because it only takes one case to show that it doesn't work to prove that the whole thing is false. So let's find a counterexample for each of these conjectures. So each of these is false. So we're going to show why it's false. Two adjacent angles form a linear pair. Well, it is true that a linear pair is formed by adjacent angles, but you do not have to have adjacent angles form a linear pair. And here's an example of one. And a counterexample can be a drawing. So here's my drawing of a counterexample showing that two adjacent angles do not have to be a linear pair. Here's angle 1, here's angle 2. These two angles do not form a linear pair. If the product of two numbers is positive, then the two numbers must be positive. All right, well, we know that the product of two positive numbers is positive. We know that the product of a positive and negative is a negative. But what about the product of two negative numbers? The two numbers don't have to be positive. They both could be negative. So our counterexample here is 1, -1, and -1. And really you can use any two negative numbers you want as your counterexample. Anything would work. You could do -2 and -5. You could do -16 and -48. It doesn't really matter. Just as long as you put down two negative numbers, those two negative numbers are going to be multiplied together to give you a positive, which disproves that conjecture. For C, every pair of supplementary angles includes one obtuse angle. Okay, well, that is almost true. We know that the two angles put together to be supplementary have to equal 180. So in most cases, you're going to have an acute angle and an obtuse angle, but there is one case where that is not true. And that is if we have two angles that are formed by perpendicular lines. Because two angles that are formed by perpendicular lines are right angles. And so this one is 90 degrees, and this one's 90 degrees. And so therefore, two right angles, you can either draw it, or you could just say two right angles would be our counterexample, because neither of these angles is obtuse. They're both right angles. For D, two rays having the same endpoint make an acute angle. Okay, well, here's one ray with an endpoint. Here's another ray with an endpoint. They share the endpoint, and we have an obtuse angle. So that's our counterexample. Two rays having the same endpoint do not have to make an acute angle. There's two other counterexamples that you could use. You could draw a right angle. You just have to indicate it with the box like we did up in C. Or you could draw a straight angle. That also is not an acute angle, but that is two rays. Those are opposite rays. And then in E, the temperature in Abilene, Texas never exceeds 100 degrees Fahrenheit during the spring months. Well, here are the spring months: March, April, and May. And we have in May a temperature of 107. So therefore, our counterexample is the temperature in May was 107 degrees. Boy, hope it's not 170. That would be, I would say, probably be deadly. 107 degrees was the temperature in May. That was in the spring, so therefore that's our counterexample. So let's wrap up this section with three things to keep in mind when you're working with inductive reasoning. And that is, you look for a pattern, make a conjecture, and then prove the conjecture or find a counterexample. Okay? Proving the conjecture is going to be more difficult than finding a counterexample to disprove it. But remember, inductive reasoning does deal with making some assumption to form your conclusion. And then from there we have to prove it or either disprove it. All right, that's it for section 1. Coming up in section 2, we're going to delve into talking about conditional statements.